For example, in this picture, we see a stack of coupons spaced only 1/1000th of a point apart. Here is the position on the board at that time. I have marked the dead stones, which are destined to be captured, with 2 marks. A good Go player who studies this position for a while can see that it can be partitioned into several independent regions. Although some fighting remains in each of these regions, the game is far enough along that the fight in any one region does not have any direct impact on what's happening in the other regions. However, it can be fairly hard to figure out which regional fight is the most important. To illustrate this, I'd like to focus only on these 2 regions where the battles are of special interest. To illustrate this, I've flipped the colors in the northwest corner and then moved the 2 corner regions into a 13 by 13 board. This then becomes the basis of an illustrative problem which I contrived to illustrate some of the theory. Now it turns out that a thick stack of coupons enables us to give more precise meanings to several traditional Go terms, such as sente and gote. These have to do with whether or not you have to respond to your opponent's last move. In modern nomenclature, we start with a definition of local temperature. With a very thick stack of coupons, the local temperature is the value of a coupon at which a perfect player would be indifferent between taking the coupon or playing the move on the board. This is the same position on which we now show the local temperatures of the various moves. A red temperature is a move that's good for white. A blue temperature is a good move for black. A purple temperature is a good move for either player. We have a theorem which states that when there is an infinitely thick stack of coupons, if your opponent makes a move which locally raises the temperature, you should treat that as sente and respond locally. But if his move does not have sente, then you can play well by just playing the hottest temperature on the board. I'll show you how this works out. Of course, as you play, the temperature changes. Right now, the hottest temperature on the board is over here in the southwest corner. So black plays move number 1 here. That lowers the temperature. The next hottest move is then over here. So white plays move number 2 there. It raises the temperature. Once the temperature is raised with a sente move, it doesn't matter how high it's raised to. The best move is to respond, which is what black does. Then white plays move number 4 here. The local temperature has now gone down to 11/12ths of a point. But elsewhere there are bigger moves with temperature 1, so they get played next. This one raises the temperature again, and the response brings the temperature back down. Soon the hottest point oscillates back and forth. This one went from 7/8 to 3/4. This one is now 5/6, but it goes down to 2/3, which makes the other one higher. The expert players are not responding locally. Black is busily playing in the southeast, while white is busily playing up there in the northwest. We're now down to temperature 1/3, and the game soon finishes up. There remain only a couple third-point moves and a couple zero-point moves. The main point of this example is that with the proper order of play, black gets several consecutive moves here in the southeast corner, whereas white, meanwhile, is getting several consecutive moves in the northwest corner. This problem, the only way you win it is to get the order exactly right, and the mathematics and these definitions allow you to do that. The local temperature provides a measure of how much the local score will vary among the different orthodox ways it might be played out. There could be several consecutive white plays, or perhaps first white, then black, or various other combinations. In some ways, temperature is similar to the standard deviation or variance in statistics, but in other ways, it's quite different. It's still true that each locality has a mean, which is the score you're going to get in this region averaged over all the orthodox orders in which it might be played out. In both statistics and in game theory, The mean of a sum is the sum of the means. However, in statistics, when you add up random variables, you find that the variance of the sum grows as the sum of the variances. However, in combinatorial games, this does not happen. The temperature of the sum is just the maximum of the temperatures. So we have no gain at all. I mean, the dispersion is constant no matter how many things you add up. In this sense, combinatorial games are much sharper than probability distributions. A situation which will baffle traditional players is when you have a move which is neither sente nor gote. Such a move does not change the temperature at all. Perhaps the local temperature is precisely 1. You make a move, and the temperature is still 1. It does not require the opponent to respond, nor does it decrease the local temperature. This requires a more complicated analysis, which traditional Go players don't fully understand. They want every move to either have sente or gote. They will go to great lengths to get right answers. They succeed in most cases, but their methodology is not able to distinguish between very close choices. So, to illustrate this, back in the early 1990s, David Wolf and I started composing problems which demonstrate why mathematics is more powerful for certain situations such as this one. Here is a very hard problem which was composed by David Wolf. No professional Go player who has worked on it, even for several hours, has ever managed to get it right. One 9-dan professional at the Nihon Keen in Tokyo spent 4 hours playing this position against me. He tried playing white. He failed. He tried again and failed again. So he concluded there was no solution. So we switched side. I played white and won. You see, he expected that the first move or two would resolve the problem. But no, it turns out this is sort of like walking on a tightrope, except that you don't know when you've fallen off. At every turn, the opponent has a whole myriad of moves he might make against you, and each of them requires a different global response. But there is a mathematical solution, and to give you a flavor of it, here it is. We partition the board into these various regions. The things not in these regions become irrelevant. Within each of these small regions, we find a so-called canonical form. Here they are. All these canonical values were found using only local computations. Each little region is a local problem that we can solve. We then have a methodology for adding them all up, from which we get the answer. If the answer is positive, then black can win no matter whose move is next. If the sum is negative, then white can win no matter whose move is next. If the sum is 0, which is unusual, because these things rarely all cancel out like that, it turns out that the second player can win if we use the dialect of the rules in which it costs a point to pass. And there is this other possibility, which is actually fairly common. This is a symbol that means the sum is not greater than 0, nor equal to 0, nor less than 0. In those cases, the first player can win. Well, it's very common. Positions like this are called fuzzy. So in problems such as these, mathematical Go succeeds by cutting up the board into separate regions, then doing a careful and precise analysis of each region, and then combining the results of these analyses. This is an aggressive application of the reductionist Western scientific methodology. Traditional Go masters instead favor a holistic approach. They emphasize the need to evaluate each move in terms of its impact and influence over the entire board. They are extremely good at this art, especially with respect to the sorts of situations which occur most often in the early and middle stages of a game of Go. They are superbly adept at recognizing patterns and shapes and identifying a small set of moves which intuitively look good. They are then excellent at approximating which of these moves is the biggest. On the other hand, our mathematics is able to do some of these calculations precisely. It works very, very well near the end of a typical game, when the temperature is low.